Welcome back. Last time, we looked at a problem involving a constrained random walk on a 2D grid. Today, we will take a step back from 2 dimensions to 1 and consider a random walk on a line. More random walks, you say? Indeed, not only are they lots of fun to look at, there are oodles of applications that we will see in future videos. Here's the scene for today. There are 5 points in a straight line, and being a creative type, I'm going to call them 0, 1, 2, 3, and 4. These are perhaps the houses of you and your friends, with a walkable block in between each house. Now, you start at point 0, your house, and you want to get to point 4, the house of your best friend. How many blocks do you expect to walk to get to your best friend's house? Well, 4 blocks, right? But let's make this more interesting with a sprinkle of randomness. Every time you reach a friend's house, you make the necessary pit stop for video games and sugar. And when you step back out into the sun blinking, you don't really know which way you should be going. So you just guess. This is like flipping a coin at each point. On heads, you go right, and on tails, you go left. It doesn't matter what you flip at 0, you always go right to 1. We assume your parents or housemates will push you in the right direction. Now, let's ask the question again. How many blocks do you expect to walk to get to your best friend's house? As usual, I want you to put down the pen and just try and come up with a reasonable estimate. This might feel strange, but what you are trying to find is the middle ground between extensive calculation and random guessing. Also, this process refines your intuition, so your brain will thank you for investing the time. Pause the video and give it some gumption. Here is my attempt. I consider the question, how far to the right do we expect to move on a single flip? You might think the answer is 0, but because of how we bounce off of our own home, there's a slight bias to move to the right. Here are the possible moves that we can take at each point. With a good amount of hand waving, it looks like on an average coin toss, there is roughly a 5/8 chance that we move right one, and a 3/8 chance we move left one. Putting these together into an expected value, it follows that we expect to move 1/4 to the right on any flip. So, to move from point 0 to point 4, we're going to need about 16 of these 1/4 steps, which means 16 coin tosses. So, my estimate for the problem is that we expect 16 blocks of walking. Okay, we've made our guess, but we're a rigorous bunch, so let's prove it. We will use E04 to represent the thing we want to determine, that is, the expected number of blocks to go from point 0 to point 4. In general, we will use Eij to denote the expected number of blocks to go from point I to point J. Let's play around, step through the process, construct some equations, and see where we land. We start at point 0, and there, when we flip the coin, it doesn't matter if it lands on Batman, we always have to move to the right. This means that E04 is equal to 1 plus E14. Take some time until you believe that this is true. Now we have just made a connection from E04 to E14. This doesn't really seem to help us, but let's keep going. Well, if we're at point 1, we have a 50% chance of moving onwards to point 2 and a 50% chance of moving backwards to point 0. We can put this information into this equation. E14 equals 1 plus a half E04 plus a half E24. It's really important to understand this. The 1 comes from the fact that we will take 1 step, and after that 1 step, there is a 1/2 chance we are at 0 and a 1/2 chance we are at 2. Now you hear your old school teacher in your head, and the impulse to smush these 2 equations together compels you to do so. With some working, we get that E04 equals 4 plus E24. We could be onto something here. First, we connected E04 to E14. Then we connected E04 to E24. Let's persist. At point 2, we take a step and have a 50% chance of being at point 1 and a 50% chance of being at point 3. Like before, we get another equation and we again do the maths, and you can fill in the gaps. To get that, E04 equals 9 plus E34. Okay, I trust and believe you can finish this one off. Like before, you should be able to reason life into the equation E34 equals 1 plus a half E24 plus a half E44, and then mix it with the earlier equations to get that E04 equals 16 plus E44. And wonderfully, E44, the expected number of blocks to get from point 4 to point 4, is just a number we humans like to call 0. Therefore, we expect this random walk to take 16 blocks. Done. And our shoot from the hip estimate was actually bang on. Now, your mathematical senses might be heightened by the fact that the square numbers were popping up all over the place. This is no coincidence. In fact, you should go ahead and prove the general result, that you expect to walk n squared blocks to go from point 0 to point n. And if you want something a bit more challenging, answer me this. What is the expected number of blocks walked to go from 0 to n if the coin is biased and is always twice as likely to land on tails? Happy scribbling.